Welcome back for another deep dive.
Always exciting to jump into a new topic,
And today we're heading into the machine shop.
at least virtually.
Exactly.
Yeah.
Virtually speaking, of course. We've got this chapter from a technical guide all about machining metal alloys.
Fascinating area.
It is more interesting than it sounds, I
Oh,
promise.
absolutely.
Mm.
On a microscopic level, the things that happen during machining affect huge things we use every single day.
Okay, so let's just get right into it. Our listeners are here to really understand machinability. Like, they need to get it, whether they're prepping for a big meeting,
Important stuff.
or even just curious about how, say, their phone's smooth metal casing is made.
Yeah, I get that.
Yeah.
Understanding machinability is really at the heart of efficient and high-quality manufacturing.
Right.
And it all boils down to knowing how a certain metal will behave
Right. Well,
when you're trying to cut it or drill it or shape it, all those processes.
So this source really points out that it's not a one-size-fits-all kind of thing. It's not like you just grab a tool and go to town on any piece of metal.
Yeah, you can't just do that.
You just can't. Right.
Nope. Each alloy has its own personality, you could say.
I like that.
Some are really easy to work with.
Cooperative.
Haha, yeah. While others, they'll really put up a fight.
It's like chef, right? Trying to figure out a new ingredient.
Yeah.
They don't know if it'll slice neatly or just totally fall apart.
I like that. A good analogy.
Mm.
And machinists, they rely on their experience in all these reference tables.
They must have huge tables.
Oh, yeah.
Yeah.
And sometimes it takes trial and error just to get the settings right for a certain material.
Wow, that's a lot of pressure. So is this material factor, this FM that the source talks about,
Yes, that FM,
is that the solution, like the magic decoder ring?
you could say that. It's really all about the material's hardness, so how tough it is to scratch or dent it.
Yeah.
And then also its tensile strength. That's how much force you need to pull it apart.
So just like that, I hand you a piece of metal, you tell me it's FM, and you instantly know if it'll machine easily or be a nightmare.
Well, it definitely gives you a much clearer picture.
Like a head start.
Exactly. Like low-carbon steel, they say it has an FM of 1.2.
Okay, 1.2, got it.
Now imagine, being a machinist, and you're given this brand new alloy, never seen it before.
That's a scary thought.
Yeah, a little bit. But then you've got that FM that's like your cheat sheet.
Oh, I see.
Tells you how much of a challenge you're in for. Helps you pick the right tools before you even start.
So we're talking about saving time, saving tools from breaking,
All of that.
and just making sure that final product is good quality.
Precisely. Now, let's get a bit more microscopic. The source, it calls it chip formation. And honestly, at that tiny level, it's quite a dramatic scene.
Yeah, the source didn't hold back on the imagery. We're talking crazy pressure, heat almost 1,000 degrees Celsius.
Yeah, really intense.
And even chemical reactions
A
happen.
lot going on.
So, big picture, what's the takeaway about this whole chip formation thing?
Well, you need to understand how the material reacts to the force of that cutting tool.
Okay, it pushes back.
Yeah, exactly. The metal, it deforms under pressure. Tiny chips break off. Kind of like sculpting, but super, super tiny.
So the tool is like the chisel, and those metal chips are like the shavings.
Yes, exactly.
So are those tiny chips like clues for the machinist?
Oh, absolutely. The size, the shape, even the temperature of the chips, all of that tells a story about how the material's behaving, whether the tool is doing its job right, and just how well the whole process is going.
So you're telling me that if you're standing there and you see sparks and those long, stringy chips are flying off, that's a good thing.
It could be. Some materials, that's just what they do when things are going right. It means good machinability, a smooth cut, but,
But there's always a but.
well, what if you see smaller chips, broken up ones, or even just dust?
Ooh, that doesn't sound good.
Different things can cause that. Could be the material itself is brittle, maybe the cutting settings aren't right, or too much heat is building up. It's all about reading those clues and then adjusting things. Like, if you're ignoring those clues, it's like ignoring a smoke detector.
Okay, that's a good way to put it.
And that actually leads us to the importance of cooling and lubrication.
Yeah, the source was all about that. But I have to admit, I always thought it was just about keeping things from overheating.
Well, it's more than that.
It is.
Oh, yeah. Cooling and lubrication, they do a lot during machining. They reduce friction, they flush away all those hot chips we were talking about,
Like a tiny little car wash.
and even they help to prevent something called built-up edge, or BUE.
Built-up edge, what even is that?
So basically, it's when little bits of the metal you're cutting, they actually weld themselves onto the cutting tool.
So it's like trying to cut something with a knife that's got food stuck all over it.
Exactly. Not good.
So cooling and lubrication are like the cleanup crew. Always there to make sure the tool stays sharp.
You got it. They prevent that buildup, and that buildup can cause a lot of problems. It makes cutting harder, the finish isn't as nice, and the tool can even break. Plus, they help keep the temperature right where it needs to be so the piece doesn't warp and the dimensions stay accurate.
Wow, so they really are the unsung heroes.
You could definitely say that.
Before we started, I had no idea how much went into this whole machining thing. Like, it's way more than just picking up a tool and cutting.
Oh yeah, it's science, engineering, and even a bit of art, all mixed together. And honestly, we've only just scratched the surface here.
Well, that's a perfect place to stop for now. When we come back, we'll dig deeper into how different metal alloys act when you try to machine them.
Welcome back. We're right in the middle of our deep dive into machining metal alloys. And last time we were talking about, well, the importance of keeping things cool and lubricated during machining. Remember? Those unsung heroes.
Right. Can't forget about them. It's like, you wouldn't run a marathon in flip-flops, right? You need the right gear. Okay, yeah, I get it. Proper equipment is key. But I gotta ask,
Okay.
how do they actually do it? Like, how do machinists actually apply these coolants and lubricants? Is it like a constant spray or something?
It really depends. It depends on what they're doing and what they're working with. Sometimes it's a steady stream of coolant.
Like a waterfall.
Yeah, sort of, over the area they're cutting. Other times it's more of a mist, or they might even use special paste.
So there's a whole strategy behind it.
There is. You got to consider the material, the tool, how fast and deep they're cutting, what kind of finish they want. It all factors in.
Wow, okay. I'm starting to see how much goes into even the simplest machining job. Speaking of which, we were also talking about cutting tools.
Yeah, the tool.
And those mysterious rake angles. You were comparing it to using a razor, how the angle you hold it at makes a difference.
Yeah, the rake angles, they're crucial. They dictate how the tool interacts with the piece you're working on.
So remind me again, how do those rake angles actually affect things?
Okay, so the basics. There are two main rake angles. Axial rake, that runs parallel to the direction of the cut,
Okay, got it.
and radial rake, that's perpendicular to the cut.
Visualizing it now.
Good. So now the question is, how do you pick the right angles for the job?
Yeah, that seems tricky.
It's a balancing act, really. Got to think about the material, the finish you want, even how long you need the tool to last, like a larger positive rake angle. That
Okay.
can often mean less force needed for cutting and a smoother result.
Makes sense. Sharper angle, smoother cut.
But there's a trade-off.
There's always a trade-off.
Larger rake angle can also make the cutting edge weaker. Think about chopping wood with a razor-sharp knife.
Oh, yeah, not gonna work.
Might cut for a bit, but then that blade's going to break.
So it's about finding that balance then, right?
You got it. Efficiency, but without sacrificing the tool.
Huh.
And that's why there are so many different rake angle combinations out there. Each one is designed to, work best for different materials and different jobs.
It's amazing, these tiny little details having such a big impact. It really is a science.
Absolutely. And we haven't even touched on all the different types of materials they use for cutting tools, all the coatings and shapes. That's a whole deep dive in itself.
I believe it. I'm definitely getting a whole new appreciation for how complex all those perfectly machined parts we see every day really are. But let's switch gears a bit.
Sure.
We talked before about chip formation, right? And how those tiny metal bits can tell you what's going on during the process.
Oh yeah, the chips.
Can we get into that a little more?
Absolutely. It's like a detective at a crime scene looking for clues. Each chip tells a story about how the tool, the material, and all those cutting settings are interacting with each other.
Okay, I'm intrigued. So what kinds of chips are we talking about, and what are they telling us?
So broadly, there are three main types: continuous, segmented, and discontinuous. Continuous chips are the long, unbroken ones, those spirals or ribbons. You often get them when you're machining ductile materials like low-carbon steel.
Like those metal shavings from a pencil sharpener?
Yeah, exactly. They usually mean good machinability, nice smooth cut.
So that's good sign. What about those segmented chips? They look like little broken pieces, right?
Yeah, like a chain of pieces. Segmented chips are basically continuous chips that are fractured into smaller bits. Happens when there are higher cutting forces, the material is tougher, or there are vibrations.
So like a warning sign?
Yeah, could be. Suggests more stress on the material. Might lead to tool wear, surface problems.
Okay, got it. And then we have those discontinuous chips. Those look like a pile of dust almost.
Yeah, those are the ones you get when the material is brittle. It breaks easily instead of bending, like cast iron or some high alloy steels.
So those are the real troublemakers.
Well, they can be. Machining brittle materials often requires a different approach, different tools, different cutting settings. Got to be extra careful not to put too much force on it or it'll just crack.
This whole chip analysis thing is really fascinating, like a secret language that machinists use.
That's a great way to put it. It's how they figure out what's happening and fine-tune everything to get the best results.
Okay, so we've covered a lot. Cooling, lubrication, rake angles, chips.
Phew.
I feel like we've just scratched the surface, though.
Absolutely. There's so much more to learn. Now, we should take a closer look at some of the specific challenges and techniques involved in machining different metal alloys.
Perfect, because I'm ready to go even deeper into this world. After the break, we'll explore the ins and outs of working with steel, aluminum, and all those other fascinating alloys. Welcome back to the deep dive. We've been exploring all the ins and outs of machining metal alloys.
A lot to unpack for sure.
There is, from like those tiny chips to the vital role of keeping everything cool and lubricated.
It's a whole world down there at the cutting edge.
It really is. And now I want to get specific. Our source, it actually breaks down how different metal alloys behave during machining. It's wild to think that, something as basic as a steel bar can have so many variations.
Oh, absolutely. Metal alloys, it's a huge and diverse world. Each material, it throws different curveballs at machinists.
So where do we even start with all this? What are the big things machinists need to think about when they're working with all these different alloys?
Well, one of the most important things is hardness.
Okay, hard.
Remember we talked about that before, how resistant the material is to scratches and dents. The harder it is, the more force you need to cut it.
So it's like you need a different knife to cut a tough steak than you do a piece of fish.
Exactly. You need the right tool for the job. And just like with knives, different cutting tools are made for different levels of hardness.
If you use the wrong one.
All sorts of problems. Bad surface finish, broken tools, you name it.
Okay, hardness, I get it. What else matters?
Ductility is another big one.
Right.
That's how much a material can stretch or bend without breaking. Ductile materials, things like copper or aluminum, they usually give you those long, stringy chips we talked about.
Like metal ribbons.
Yep. And while those chips can be a good sign, they can also be a bit of a pain. They get tangled up around the tool, clog things up.
So even when a material is considered easy to machine, there are still challenges.
Always. There are always things to watch out for. That's what makes machining so interesting, Keeps you on your toes.
Keeps things interesting. Okay, so we've got hardness and ductility. What about those materials that aren't so ductile, the tougher ones?
Well, brittle materials, those are the ones that break instead of bending, like cast iron. They tend to form those discontinuous chips, the little broken bits, almost like sawdust.
Right, those look like a mess to clean up.
They can be. When you machine brittle materials, you got to be way more careful. Can't use too much force or the material will just crack.
So you really have to understand the personality of each material.
That's it.
And adjust your approach. That's where that material factor, that FM, comes in handy.
Oh yeah, the FM is super helpful. Lets the machinist quickly figure out how easy or difficult a material will be to work with, based on hardness and tensile strength.
It's like a quick reference guide then.
Exactly. Helps avoid expensive mistakes and make sure the whole process goes smoothly. So you ready for some real-world examples?
Hit me with them.
Okay, let's start with steel.
Steel, the classic.
Yep, it's everywhere, right? Bridges, cars, appliances, you name it. And of course, there are tons of different types of steel, each with its own personality when it comes to machining.
So it's not just steel is steel?
Nope, not at all. Like those low-carbon steels, the ones with less than 0.3% carbon, they're usually pretty easy to work with, softer, more ductile. They give you those nice long chips.
So if you want a smooth, easy process, that's what you go for.
Pretty much. But as you add more carbon, the steel gets tougher, harder to machine. You need special tools and techniques then.
It's amazing how a tiny change in the makeup can completely change how a material behaves. What about those alloy steels, the ones with extra stuff added?
Yes. Alloy steels. They have other elements added, like chromium, nickel. To make them stronger or resist corrosion better, giving them special properties.
But they must be harder to machine, right?
Some of them are, definitely. Some are really tough to work with, need very specific tools and settings. But that's what makes it challenging and fun, right?
It's like a puzzle. Okay, so steel's a whole world of its own. What about, like, aluminum? That's a popular one.
Oh, yeah. Aluminum's super popular. Lightweight, doesn't rust easily. Perfect for things like airplanes and cars. And it's generally considered easy to machine.
Easier than steel.
Yeah, usually. It's softer, produces those long, stringy chips, but
It's always a but.
it can be a little sticky.
Sticky.
Yeah, sometimes you get this gummy buildup on the cutting tool. That can mess up the surface finish.
So even with a forgiving material, There are still tricks to learn.
Always. Like I said, each material has its own personality, its own quirks.
Well, this whole deep dive has really opened my eyes. I never thought about how much goes into making all those metal objects we use every day. The
Mm.
science, the skill, the artistry.
It's a whole hidden world.
Yeah.
And it's thanks to all those skilled machinists out there that we have all these amazing things.
Yeah, I'm going to look at everyday objects a little differently now.
I hope so.
And next time I see a scratch on my phone, I'll remember all the work that went into making it.
Exactly. Remember the process, the people behind it.
Absolutely. Thanks for taking this deep dive with me into the world of machining. It's been fascinating.
My pleasure. And remember, there's always something new to learn, something hidden beneath the surface, waiting to be discovered.
Great advice. Until next time, Chint exploring.